Howdy and good day. We're in algebra covering CO7, converting from scientific notation to standard form. I always thought that this should be taught in science class, but it does have some mathematical pieces to it, so I suppose we'll do it here. Fun fact, did you know that the Earth is 491 billion feet from the sun? We're learning a fun fact about the Earth and the sun. 491 billion feet away. Let's write that number again. 491 billion. That's a lot of zeros. 9 of them, in fact. That's how I make us write it again. No, it's billion. And again. Is this important? Yes.
Yeah, so you can just do like 0 to...
If you're writing an essay about the distance of the sun from the Earth, you might have to write 491 billion, something like 491 billion times. Would be a lot of work. So all of your unsolicited complaints are why we have scientific notation. Right? It is a way to represent very large or very small numbers, which you deal with often in science class. Do you have something for the group? Oh, okay. In a more concise way. Okay, warning for you. So scientific notation is a way to write very large or very small values, and here's the math piece of it, using powers of 10. Okay, using powers of 10. Luke.
I do have a question for this though.
Yeah.
So for the stuff billions, we would just track that. We just track all of the zeros and be like 10 to the it should be like 10 to the power of 9.
We'll talk about that. It's not 10 to the 9th power, but you're heading in the right direction. Olivia. Like the definition of it? No. Okay. So what we mean by using powers of 10 to write this a different way, Luke kind of said, well, if we take off the zeros here, there are 9 of them. So would we just multiply by 10 to the 9th power? The answer is kind of. You do get rid of all of the zeros, but the other rule for scientific notation, and I've got no better place to write this, but up at the top here, you can write wherever you want. But the other rule is that you need to have your decimal point, okay, with only one non-zero number coming before it. So we wouldn't want 491 times 10 to the 9th. We want 4.91 times 10 to the 11th, right? Because we got rid of the 9 zeros by moving the decimal point 9 times, but then because we moved it 2 more times, right, to get between the 4 and the 9, that's why it ends up being 11th power. And what this is telling us, because when we multiply something by 10, what's really happening is the decimal point just moves one spot to the right. That's why 2.5 times 10 is 25. Just kick the decimal over. What this is telling us is that in order to get back to our original number, which is 491 billion, we're going to multiply by 10 or move the decimal point to the right 11 times. It's a lot of times. Okay? Luke.
If you were to do this in equation, then you should go for around the 10 and the 4.91.
No, because 10 to the 11th power is a number. It's a 1 with 11 zeros after it, right?
But I'm saying if we want to solve this like term dots, wouldn't we have to do like 10 times 4.91 first, then have 11 go?
Actually, if we put parentheses around 4.91, that would mean, and don't write this down because you don't want to do this, but if we did, that would give us 49.1 to the 11th power. which is going to be something totally different than 491 billion. So no, we do not want parentheses here. The order of operations is correct in that we're taking 10 to the 11th power and multiplying that number by 4.91 to get back to our original. Okay? Is this still the review realm?
Yes.
Last class said you kind of covered it before, but there are some things to worth refreshing. Okay, so rewrite in scientific notation. We've got 5,670,000. What two numbers will our decimal point go between? What two numbers will our decimal point go between? Noah? 5 and 6. And then our 7 is going to follow as well. All the zeros do end up getting dropped off here. Okay, but how many times do we have to move that decimal point to get from 5.67 back to where it is in the original number? Right, Nick?
Times 4. The exponent of 4.
Well, if we move the decimal 4 times, 1, 2, 3, 4, we're not quite between the 5 and the 6. Right? We got to move 2 more times, and so it's going to be times 10 to the 6th. And you can check yourself here, because if you were going back to the original number, if you're going from scientific notation back to standard form, if we've got 5.67 times 10 to the 4th, we only move it 4 times. Well, that's only 56,700, right? We do need to move it 6 times to get back to the original number. So don't just count the zeros and have that be your exponent. Okay? It's how many places to get where we need it to be. So there's only one non-zero digit beforehand. 878 trillion. 878 trillion. What two numbers is our decimal point going to end up being between? Sebastian? 8 and 7. Well, if it was the second one, it would be between 7 and 8, right? So it'd be 8.78. And when you're dealing with super large numbers such as this, commas can actually be kind of helpful, right? Because rather than counting each individual hop, you can kind of go by threes. Every comma represents 3 moves, right? So 3, 6, 9, 12, and then 13, 14 to get between the 8 and the 7. If you put an exponent of 12, right, you forgot that you've got to still count those jumps to get so there's only one non-zero digit to the left. Okay. The next 2 examples have to do with when your number is very small. 0.00013. What 2 numbers do we want our decimal point to be between? Yeah. The 1 and the 3. How many jumps to get it there? 1, 2, 3, 4. Right? Lily. That's why I called on you. Yes. And our exponent's going to be negative here because to get back to the original number, the decimal point goes left. Okay, it's like we're dividing by 10 4 times. Every time you divide by 10, the decimal point gets moved to the left. And we have to do that 4 times to get back to 0.00013. Okay. No loss. The last one here, we're going to put the decimal between the 4 and the 9. To get there, 1, 2, 3, 4, 5, 6, 7. So 4.901 times 10 to the negative 7th. So you should see a definite difference here, Sebastian. Go ahead.
So when you go backwards, you don't do the number, you do the 10 instead of, you do the number as the exponent and the 10 as the whole number?
When you go backwards, what do you mean?
Never mind. I was getting mixed up.
Okay. So we see a difference here between when our exponent is positive and when our exponent's negative, right? What does a positive exponent mean? Or why is it positive in the first 2 examples? Luke?
I'm pretty sure it's because you're going up and trying to get. Well, I thought I had it for like going backwards, just because You need something to go like before the point zero something, so it's like positive.
Okay, you kind of jumped around. I think you're dancing around the. Noah, what were you gonna say?
Because it's a whole like positive number.
It's a big number, right?
Big.
And when our exponent is positive, that means we are multiplying by 10. And when you multiply by 10, the decimal point goes to the right. And that's how we get back to our original number. Starting at 5.67, if we want to turn that into a number that's big, we've got to move the decimal point to the right. Like a number line. Okay? And that's why it's 10 to the positive 6th. Whereas for a negative power, your original number is going to be small. Okay? Because like a number line, right? Negatives are to the left. When you have a negative power, to get from 1.3 to 0.00013, that small number, you've got to move the decimal to the left. Okay? So positive power, your number's big, going right. Negative power, your number's small, going left. Yeah?
Wouldn't it be the opposite because the decimal is at the end of the zero, so it's going like to the left to get to the decimal, and then for the negative, it's going right to get to the.
But it's looking for how you get from scientific notation back to the original number. Because in scientific notation, up until the exponent, they all look exactly the same, right? 5.67 times 10, 8.78 times 10, 1.3 times 10, they're all the same. This exponent tells you how to get back to your original value. Okay? So for the next section, where we rewrite these numbers in standard form, 7.613 times 10 to the positive 4th, is this number going to end up being a large value or a small value? Large. Because we got a positive power, which means we're multiplying by 10 4 times, or moving the decimal to the right 4 times. Right? That extra empty space that we have there gets filled in with a 0. And so our original number is 76,130. Okay? Olivia.
Wait, so for the negative ones, after you like find how many spaces there, do I have to put like a 0.0 because like it's up there as well?
Yes, these are going to all be decimals that start with 0 point something. Yeah.
Does the 10 matter when you're doing these?
Like the times 10?
No,
Right? Or the
10, like not the exponent, but like just the 10.
that?
Yeah.
Well, 10 to the 4th power is 10 times 10 times 10 times 10, right? So this just tells you how many times you're multiplying by 10, which is how many times the decimal point moves to the right. Because whenever you multiply something by 10, that's what happens. The decimal just gets kicked over. You're going to the next place value. Okay? So 6.8 times 10 to the 10th, we're multiplying 6.8 times 10 times 10 times 10 times 10 times 10, 10 total times. Which means this decimal gets moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total times. And all those empty spaces become zeros. So this number is 68 billion. Okay, as a value. The next two, having negative powers, we're dealing with values that are actually quite small. Okay? They look just like the first two we did up until that exponent. The fact that the exponent's negative means we're dividing by 10 7 times, or moving the decimal to the left 7 times. So 5.1973, that decimal is being moved to the left 1, 2, 3, 4, 5, 6, 7 times. And again, all those empty spaces get filled in with zeros. So our original value is 0.00000051973. Like we are talking about the size of quarks and molecules and atoms and things that are super, super, super small. Okay. Alan, question?
No.
Okay. Finally, 8.21 times 10 to the negative second. I entered the page on a short one so we can fit it here. Okay. But we're moving the decimal to the left because the power is negative. It's moving twice, dividing by 10 twice. Fill in our empty spaces with zeros. And we get 0.821. 0.0821. Yes?
What would happen if you had like a negative one or a positive one? Would it only move or?
A negative, like negative 8.21 times 10 to the negative?
No, like 10 to the first power, 10 to like the negative first power.
10 to the negative first would just be like dividing by 10 once.
Okay.
Like if we had, I'll put it up here in the middle. Ooh, keep you in suspense.
These are your Thursday afternoon announcements.
So the question was asked here about something like 10 to the negative first. That would just mean that you're dividing by 10 once. So if you've got something like 2.5, okay, times 10 to the negative first, that would just be 0.25. Divided by 10. Just gets moved over once. So, any more questions on this? Front side or first page? There is a second page. The second page is where you get to show me how well you understand this, or at least get to practice it. The first 8, they're given to you in standard form. You need to rewrite them in scientific notation. So kind of like what that first practice section was on the front side. And then these are in scientific notation, and so you need to write them in standard form, what that second section was. Yes? The last one, our first opportunity for a little fun fact from my avatar there. At the time of this document's last edits, I was about 1.133 times 10 to the 9th seconds old. Okay? So if you use scientific notation, apply it to that number, that's how many seconds old I was. Seconds. It's a big number because seconds don't last very long, and I'm pretty old. Okay? Your job is to convert that number of seconds into days. Okay? The question is not, Camden, shh. Folks, shh. The question is not how many seconds old I am. The question you need to answer is how many days I am. So to convert from seconds to days, there are a couple different ways you can do it. You just need to remember how many seconds are in a minute? 60. How many minutes in an hour?
60.
How many hours in a day?
60. I'm a little struggling.
That's okay. So that's make sure you are answering the question that is being asked there. How many days old, not how many seconds. All right. This is going to be due tomorrow. You also have con due tonight, but you have literally the entire day to finish it. Football picks are due tonight as well. Football picks are due tonight as well.
Who's number 1?
I don't remember.
Sophie something.
Yeah, Sophie something. All right, folks, that's how you math.
Don't forget to like